Okay, Bismillahirrahmanirrahim. So we are, yeah, please. Oh, it's not. Is that better? Oh, okay, great. Let me see if the recording is on. Yeah. All right. So we started talking about features, and in features, the first feature that is the simplest to understand is edges. So we started talking about edges in the last lecture, right? So we said edges are locations of intensity variation, right? So they are locations where intensity changes rapidly, right? And what that really means is another way to say the same thing, locations where intensity changes rapidly. So another way to say the same thing is that the rate of change of intensity is high. And we know how to measure the rate of change of something, that's differentiation. So in continuous form, this is what differentiation means, right? Uh, in continuous form, this is what differentiation is. You take a small step along your function. So therefore differentiation is a directional operator. There is some sort of direction associated. In this case, that's the x-axis direction. So you take a small step in the x-axis direction. So this is derivative with respect to x, and then you see how much the function changes. The function in this case is your pixel values. Okay, so you see how much the function changes, and then you divide that by the step size, and then you ensure that the step size is as small as possible. Is the display correct now? No? Yeah, I don't know where the aberration is coming from. Okay. Um, and then in discrete form, well, the smallest step size, the smallest non-zero step size that you can take is 1. And so we substitute delta x is equal to 1. And so this is what you get in the discrete form. Okay. And so therefore, the discrete derivative can be written as a convolution. Remember what is convolution? You take this mask and you slide it over, and then you multiply the weight with the value, with the pixel value, and you sum that up over the mask. Okay, so since I want to subtract a pixel from its previous pixel, we chose this mask to be 1 minus 1, and if we convolve with this, then that would be a derivative, a discrete derivative. Agreed? So we discussed the convolution operation yesterday, and it's a very fundamental operation, not just to implement different types of filters, but as we will see in deep learning, when we discuss deep learning, we'll see that convolutional neural networks are also like a fundamental part of why deep learning is getting so much attention right now. So therefore, convolution is a very important operation to understand, and it's really quite simple. It's point by point multiplication. You try all locations. You do point by point multiplication and sum. So it's a multiplication plus an addition operation, and in that sense, it's a linear operator. Convolution itself is a linear operation because it's just multiplication and addition. Okay. All right, so once I know how to find the derivative, I can even find the double derivative just by applying the same mask again. Okay, so I showed you this example. This is a picture. I can find the derivative in the x direction. Now remember, my x direction is going vertically downwards. That's the convention we use. So therefore, I'm using a +1 -1 mask like this to get this picture. Okay, and what this does is it highlights variations, edges which are going in this direction. So if I have a vertical mask, it will highlight horizontal edges like maybe this edge here, or if you see this edge here, and so on. But there is an edge here of this house also, but that's not highlighted because the mask is in this direction. So it will highlight edges that go across the mask direction but not parallel to the mask direction, right? Because that's the measurement it's doing. It's subtracting this pixel from that pixel. So if those pixels are different, then I'll find the edge, which means the edge is going this way. Agreed? And I can do it in the other direction. So in this case, my mask is +1 -1 like this, and so you see that these edges are highlighted, but the horizontal ones are not, which were highlighted in the previous image. They are not. Okay, the color coding here is that because I get plus and minus values both, I've just scaled them to 0 to 255 scale. So the middle value, the middle gray is about 0, it's close to 0. And then the positive numbers are white and the negative numbers are black. So it's a continuous structure. Yes, we have a question. So you are saying I apply the mask first along the x-axis, and on the result I apply the mask on the y-axis. Well, that's a double derivative. It's a partial derivative of a derivative. So that's not a single derivative. That's a double derivative. So what you would get is really the y derivative of the x derivative, which means you would actually be differentiating this image and not the original image. So that would definitely be different. It's like a weird structure. I mean, it's not a single. Here I'm showing you single derivatives. No, it won't. It won't, because it would be the derivative of the edge in the other direction. Okay. Yes. Oh, so the question is, once I have convolved, can I go back to the original image? What do you think is the answer to that? Yes. How? Uh, okay. So one approach is, yes, it should be possible because it's a linear operator, and so we should be able to invert it. Yes. No. Maybe. No. Why no? Okay. Yes. So that's one argument. We have taken the derivative, so it will require an integrator, and to construct from an integrator, you need a constant, and that constant is unknown. So yeah, you should not be able to do this in general. Uh, in general, convolution is not easy to revert, right? Because what happens in convolution, you do a point by point multiplication and then you sum that up, and then you only know that sum number in the result. So it's kind of like saying I summed two numbers and the result is 50. What were the two numbers I summed? That doesn't have a unique answer, right? And now they depend on the mask. So if I know the mask, even then it's not a unique answer because the underlying data is unknown. And there might be several combinations, especially in a large mass. There might be several. Now, people have ways to invert it. In signal processing, you study about deconvolution filters, but the solution is not unique. Deconvolution filters always work under some assumption of the underlying data. They have to take some strong assumptions about the underlying data to be able to reconstruct it. In general, convolution is not a invertible process. Okay. All right. Okay. So you get a sense here of this is the image. So really, if I in mathematical terms, if I want to write this image, I should write it as, if the image is I should write this as partial derivative of I with respect to x, right? Because it's your image is a two-dimensional function. So this is multivariate calculus. When you study it in your course, the image is a two-dimensional function, and I'm taking the derivative in one direction, which is x. Okay, and similarly, this is also the first derivative. It's not the second derivative, it's the first derivative. This is partial derivative of the image with respect to y, and I'm taking the derivative in this direction, the y direction. Okay, so these are your two partial derivatives. Okay, so now I'm going to do this. I showed you what the derivative means as a discrete derivative, and I'm going to do this a bit more formally and introduce a few more concepts which are very important. So we understand that the edge is a place of rapid change of intensity function. Okay, so if I look along this line, the edge looks like this. In this ideal image that we have created, this is what the intensity function looks like. And if I differentiate this intensity function, well, what's going to happen? Here the derivative is 0, right? Because I'm like the slope of this is 0, so that's the slope. And then here the slope becomes rapidly negative. Okay, so that's here, and then so this is the slope. That's the maximum slope. That's here, and then it becomes 0 again. Here it becomes 0 again. So I'm climbing back to 0, and then it remains 0, and then this is the, so basically this function is the derivative of this function. Okay. Now, so these peaks in the derivative function, this negative peak and this positive peak, these peaks in the derivative function are really what gives me the edge. Okay. All right. So here, this is a real image now. That was an ideal case. Here is a real image. So this is the intensity function. I showed this to you before. And so this is the derivative of that intensity function. And you realize that there are strong peaks in the derivative. And these are the ones that will correspond to edges. Okay. And now each edge is a different strength because of how much color was changing there. Okay. So that's what you see here. Okay, all right. But what happens is one of the real problems in doing this computation. Yes. No, so there are two derivatives there. There is the x derivative and the y derivative. The x derivative will get different information and the y derivative will get different information. You do compute derivative at every point, so you know that this is the derivative here. But the derivative at that point is really an x derivative and a y derivative. So it's not one value because the function is two-dimensional, so you get two derivatives. If the function was three-dimensional, you should have gotten three derivatives. Okay, so in fact, really you can compute derivative in any orientation. Those are called directional derivatives by taking a dot product with that direction. But we normally do that in orthogonal direction, so that's the x and y derivative. Okay, in fact, you guys are familiar with the gradient vector. The grad vector, which we write as delta, inverted delta symbol, right? The nabla symbol. So the gradient vector is just exactly this: the partial derivative with respect to x and the partial derivative with respect to y if you have a two-dimensional function. Okay, so that's really what I'm showing you visually. All right. So now one problem in computing derivatives, I showed you those edges, right? They appear as peaks in the derivative. But if you have a bit of noise in your image, here we added a little Gaussian noise. By Gaussian noise, I mean normally distributed random numbers. Okay, so these are zero mean, but some variance, not random numbers. So they add or subtract to the pixel value. Okay. Now, if you add your noise, this is what the derivative looks like. Since the derivative is looking for differences, if you have noise, those differences will also be enhanced. The derivative really is the rate of change. So it enhances in the derivative signal, those places where a change is happening get enhanced. And now noise is also a form of change, so noise also gets enhanced. Okay, so this signal now is a bit noisier. Okay, just to show you in one dimension for an ideal case, let's say this is a noisy signal. Okay, if I compute, so there is clearly an edge here, which is a sharp change in intensity. So this is like, it's dark in the beginning and then it's bright later. It's like one line, but there is some noise on this. So if I find the derivative, it comes like this. Okay, and now where is the edge? I have a hard time finding that out because there is just a bunch of noise which got enhanced and it kind of is hiding my edge. Yeah. Okay, so the question is the slope with the edge on it, isn't that going to be really big, right? And yes, indeed, if so notice the scale here, right? So indeed, if I was computing the derivative and I was subtracting this pixel from this pixel, then yes, I would have gotten a large peak, right? But this edge is spread over several pixels. And so really what I'm subtracting, when I'm here, I'm subtracting this with a very nearby pixel. And when I'm here, I'm subtracting this with a very nearby pixel. Right, and all of them have noise in them, and so the noise signal, I mean the derivative signal looks, I mean this is the actual derivative, right? I don't see actually that large jump here for two reasons. Once I have a noise, and the other that the edge is spread over some distance. Okay, so this is a real problem actually in computing the derivative the way I described it, just by a +1 - 1 filter. That works well in ideal cases, but your images are not never ideal. They always contain some noise in the pixel values. Where does that noise come from, by the way? Well, it comes from all sorts of sources. It comes from, uh, well, the world itself is noisy. Well, that's not noise, but really this surface is not just one smooth color. It has its own color variation. Okay, uh, but then when light strikes this surface, it gets reflected, and my sensor measures that, and the sensor has its own thermal noise. It even with the same light intensity signal over time, it won't give me exactly the same pixel value. It will give me something around that, right? Because these are physical measurements. So there is always noise in your imaging pipeline. Okay, and then your image might be compressed in a lossy fashion, like very popular JPEG images. The JPEG images themselves will generate some, they will introduce some noise in the picture because they will distort the color values slightly so that the image can be compressed more. Okay, so there are lots of sources of noise in the imaging system. So even if you take a perfectly white, let's say, sheet, and you have perfectly uniform lighting, and you try to image it perfectly with a vertical camera so that all things are equal, even then you won't get all exactly the same values in the image, surely. Okay, and that's noise. Lighting itself introduces a change in shade and so on. Okay, all right. So because of this problem, the filter that I described you, the convolution mask that I described you, is not incredibly useful in practical scenarios if I want to find edges. Okay, so what might I do? Any ideas? I could, okay, so that's a good point. Because the edge is spread over a larger area, what I could do is I could spread out this +1 and -1 in my mask, make the mask size larger. There's a +1 and a -1 here and a lot of zeros in the middle, so that I'm subtracting two far away pixels. So this is an issue of mask size. I might not use I might not use the smallest mask size that is actually the true derivative. I might increase the mask size, and then that will look for larger variations in the sense that will have the capacity to look for larger variations. So yes, indeed, that's possible. I can use it. It does come with a problem also, but that's a fundamental problem. We can't like do much about it in most of the cases, which is that if my mask is very large, then I will find this edge, but this edge, in the edge signal, the edge peak will be broader, and that means I'll have difficulty localizing where this edge exactly was in the image. So detection and localization often go as there's an inverse relationship between them. If you use bigger masks to enhance your detection, your localization of the edge is often affected. Okay. Any other idea? Uh, that's exactly what we said. I mean, 3 by 3, I don't know, but I'm saying because we are differentiating along a line, I can use a bigger mask along that line. Okay. Why would that have an advantage? Why would that have an advantage? Why would that solve this problem? I mean, I'm talking about a one-dimensional signal right now, so there's no issue of bigger mask. But even in two-dimensional signals, why would that have an advantage? I mean, I don't know why. What he said makes sense. I can spread out these two values, right? But adding this way, I mean, people do that, but I'm asking you, why would that make sense? Yes, you said something here. Yeah, okay, so that's like the standard way to do it. I can apply a noise reduction filter to smooth out this signal before I find the edges. And in fact, just to come back after this comment to your comment, when people have masks which are two-dimensional, the idea is to smooth along one dimension and to differentiate along the other dimension also. So people do that. There are some famous derivative masks like that. Yeah. Yeah, but the sharp decrease happens over a range. That's exactly what's happening here. I really don't see how you would do that with a derivative, right? I'm just showing you the derivative. So this is a signal. What do I do with it now? What do I do with it? Yeah. Yeah. Okay. What is that? Okay, it's a lot simpler than what you're trying to do. He said, let's just smooth this signal, okay? And this is what we practically do almost always while doing edge detection, okay? Now the argument here is difference filters like derivative filters respond strongly to noise, and so image noise results in pixels that look very different from their neighbors. Generally, larger the noise, the stronger the response of the derivative filter is. Okay, so what can we do about it? Well, this is your signal with noise. Okay, there is a sigma is equal to 50 Gaussian noise added to zero mean standard dev is equal to 50 noise added to this signal. Okay, so that's what makes this ideal signal jiggle. And then what I did is I took a Gaussian filter, or I could have used an average filter, but this is a Gaussian filter. This is also a mask now, but this is a mask such that the value at the center is higher and it decreases. So it's a Gaussian function. Okay, and I convolve the original signal with this function. Okay, so what happens is I get this as a result. Now what is the Gaussian doing? The Gaussian is really like, when you convolve it, it's really like averaging neighborhood pixels. Okay, but it's averaging such that when it averages at a particular location, it gives more weight to the center pixel and lesser weight to as the pixels go away. Okay, that's it. Okay, yeah, as a function, this function g is there is some constant here, which is 1 over square root of 2 pi sigma, but that's just a constant. Then e to the minus x square over 2 sigma square. Okay, so that's what the function is. So sigma is a parameter. This is a parameter which appears in the denominator of this exponent. And so if you change sigma, if you increase sigma, the Gaussian gets fatter. If you reduce sigma, the Gaussian gets thinner. Okay, so I use this as an average filter, as a smoothing filter, and I apply that to the original signal. So this f convolved with g gives me this. Okay, yes, there's a question here. Yeah, okay, so that's a good question. How do you choose sigma? And there is not a very good answer to that. There are many different answers. So let me you need, so let me first qualitatively answer that. You need enough of a sigma to suppress noise, but not too large to actually distort your edges, to actually suppress your edges. Okay, so now that's not a good enough answer. I mean, you might have to try a lot of different sigmas for your problem. Actually, the answer depends on how fat an edge are you expecting in your image. Okay, and if you know the answer to that in pixels, then you can have a precise relationship for sigma. Okay, if I expect edges to be this big, then this is the sigma I should use. Okay, but often in images there are some very thin edges, some very fat edges. It's a whole mixture, and so people sometimes apply different sigmas and get edges at different levels, like build a hierarchy of edges. These are the thin edges, these are the fat edges, and they use all of them together. So there are lots of different things that people do It's not a very clean-cut answer here that this is the optimal sigma to use. No. All right. Okay. So once I have this, I can now take the derivative because I have a smoothed out signal. I can now take the derivative of that smoothed out signal. This is d by dx of f convolved with g. Okay. And now that should really give you ideally a peak at the edge and not anywhere else because I have suppressed the noise sufficiently. Okay. Any questions on that? Is that idea clear? So I'm using two filters. I'm using two convolutions. One's first to suppress the noise and then to find the edges. Yeah. Okay, let me come to that of how they look like. Yes, it depends on the filter sizes actually. So you might get very blurred output out of this. Okay, all right. So now that I've introduced this idea of convolution and how you how you find edges in one dimension, let me now formally write it in 2 dimensions. Okay, because we are dealing with image entities in 2 dimensions. So your gradient really, your derivative really is a gradient vector now, because it's a 2-dimensional field. The image is a 2-dimensional field, and so the gradient vector. So I write this as nabla I, and this boldface x really is x, the vector xy, which is your pixel location, which belongs to R2, right? That's what we were discussing in the previous module a lot, which was the location, right? But now at every location you have an I, which is the pixel value at that location. So that pixel value will be indexed by a 2 vector, which is this x. And now this nabla symbol defines the gradient operator, which is the 2 derivatives, the partial derivative of I with respect to x and the partial derivative of I with respect to y. Okay, so that's the gradient vector. Where the partial derivative of I xy with respect to x is, in the continuous case, it's this definition, right? I'm taking, to find the partial derivative in x, I'm taking a step in the x direction and not in the y direction. And to find the partial derivative in the direction of y, I'm taking a step in the y direction and not in the x direction. Okay, straightforward, right? So that's the definition of the gradient vector. And one of the things that you have studied in calculus is that the gradient vector points in the direction of maximum increase. Okay, so it's actually a pretty interesting vector, right? Because think about the gradient vector as, let's say you went to the hills and you are standing at a particular location on a hill. Okay, so you ask what is the direction of maximum increase on this hill, right? Now there are 360 degrees around you. That direction could be anywhere, right? So one way to measure that is, okay, take a step in this direction and see how much you increased. Then take a step in this direction, see how much you increased. Take a step in this direction, try all possible directions, and then figure out which one afforded you the maximum increase. That would be the gradient direction. But actually you don't have to do that. You don't have to try all possible directions. All you can do is just take the step in 2 orthogonal directions. Okay, you can do this on only 2 steps. Take one step, let's say this way to the right, and figure out how much you increased. It has to be a small step, by the way, for it to be gradient, right? And then take a step this way and figure out how much you increased. And then from that, arrange that as a vector and just find the direction of this vector. Okay, and that will be your gradient direction. It might be somewhere in the middle of those. All right. So that's the notion of gradient vector. The gradient vector points in the direction of maximum increase. That's why you have, in optimization, you have gradient descent algorithms. Gradient descent algorithms always take a step in the negative of the gradient direction because they want to reach the minimum of the cost surface. Okay, so gradient is the direction of maximum increase, so minus gradient is the direction of maximum decrease, and that's why on a continuous surface, and that's why they take a step in that direction. Okay, so they are very popular optimization techniques. In fact, we'll talk a lot about gradient descent when we come to neural networks, because that's a crucial part of backpropagation algorithm. Okay, all right. So this is just to visualize what gradient looks like, and I took this image from Wikipedia, so their coloring is a bit different from what we do. What we normally do is white is higher values and black is lower values. In this image, black is higher value and white is lower value, so it's just an invert. But this is what the gradient vectors at every point in this image field look like, because they are all pointing in the direction of maximum increase. If the image field was like this, they will all be pointing this way. Okay, there's a gradient vector at every location, and it's just the concatenation as a vector of the x derivative and the y derivative. Okay, so in this case, it makes sense that they are all pointing this way because there is a derivative in this direction, but there is zero derivative in this direction. This function is just not changing in the vertical direction, right? All right, any question? So that gives you a notion. One of the things that I'm doing in this course is that almost all the mathematics that we are doing, you have seen this before. The fundamentals of this mathematics, you have seen this before. But I want you to build a mental picture in terms of images of what that means. That's why I'm telling you what a gradient vector is. Of course, you have seen gradient vector in calculus. But on an image, what does it mean? That's what you should immediately have a picture in your mind. Okay, so as an example, this is a function. Okay, this function is x e to the minus x squared plus y squared, and I've color coded that function. So the underlying colors are what represents the function. The function really has a dip here and a peak here. Okay, it's like this part, the green part is level, and then this is like a trough, and this is like a peak. That's what this function actually represents if you plot it. Okay, and I plotted gradient vectors everywhere. So the vectors are coming out of this trough because they want to climb to the maximum value. So every vector is looking at its local neighborhood because you are doing a derivative. So the derivative just compares local pixels, right? So they are looking at their local neighborhood, and the gradient direction is really the direction that will climb you the fastest out of this trough. And then here on the peak, it's the vector which will get you to the peak. So these vectors are pointed this way, and these vectors are pointed this way. They are all pointing to the peak. So that's a visualization of what gradient vectors mean on a function. Yes. Gee, red is higher, blue is lower. So if I were to draw, let's say, a cut through this function, it would look like this. That's what this function is. In fact, actually, this function is the derivative of a two-dimensional Gaussian in the x direction. A two-dimensional Gaussian is a two-dimensional circularly symmetric Gaussian is e to the minus x squared plus y squared over 2 sigma square. So I just put sigma is equal to 1, and I took this function and differentiated it, and as a derivative, I get an additional x here. So that's what this function is proportional to. It's actually a derivative of a Gaussian function. This is a Gaussian function, and that's its derivative. Okay, remember, why is this the derivative? Because the slope was 0 here, and then it started getting to a negative slope, a maximum negative slope here, and then it started coming back to 0 slope, which is here, and then it started going to positive slope. This is the positive line, so that's maximum positive, and then it started coming back to 0, right? So that's why it's like this. Yeah. Yes. Yes. No, I just colored 0 as green. I mean, that's my choice. I have a color spectrum here going from blue to green to red. Okay, and red is highly positive numbers, blue is highly negative numbers, and green is at 0. So whatever I color coded, that's my choice. So that's how I color coded it. Okay, is that clear? So that's the notion of a gradient vector. Okay, so here's an example. So I took an image. I really took a small image so we can see all the vector values if we kind of want to plot them. But this is an image. So it's like a 60 pixel by 80 pixel, 60 rows, roughly 60 something rows, 80 something columns. Okay, and now so this is what I call I of xy. The actual matrix of pixel values that you will get. That's I of xy. That's your function. Okay. And so what am I going to do? I'm going to convolve it with a mask like this to get the derivative in the x direction, because my x direction is vertical. Okay, so that really will give me just I of x plus 1, x plus 1 comma y minus I of xy. That's all it will give me, right? Which means I will be subtracting every pixel from its preceding pixel. Okay, and so I call this partial derivative of I xy with respect to x because it's in the x direction, and this is what it looks like. Okay, again gray is close to 0. Then there are some positive values and negative values. So positive values are going towards white and negative values are going towards black. I just use MATLAB image sc command, so that takes all your data and scales it between 0 and 255 to plot it in the image. Scaled image view. Agreed? Everyone is perfectly clear how I did this? There's a conv2 function in MATLAB. You can use that to implement convolution, or you can write your own routine that does this multiplication. Okay, and then what I can do, this is just one part of the gradient vector. This is the first term in the gradient vector. What I can do is I can do another convolution with this mask. What would that really be in mathematically? That would be I of x y plus 1 minus I of x y, because this is in the y direction, and as a symbol I call it partial derivative of I x y with respect to y, and this is what it looks like. Yeah. Of course, if you want, you can add those images, but that would be, what would that be? I mean, what I'm really after actually is the gradient vector, and I'll merge the gradient vector into one image in some other way, because that's how we do vectors. When think about a vector, you have values in that vector. You don't add all of them up and say that's some entity. Well, it is some entity, but is it a useful entity or not? Okay. So typically what do you do that? If you want to give me some estimate of the size of that vector, typically what do you do? You can find the length of that vector, the norm of that vector. That would make more sense if you wanted to merge that. Okay, the magnitude of the vector. Because gradient essentially is a vector entity. Okay, in multivariate functions. All right, is that clear? Is the you can implement this in MATLAB quite simply, right? Okay, and now because we understand that derivatives are sensitive to noise, we will actually not do this. We will smooth before we differentiate. Okay, just so that so essentially what we do is we take this image, and first I convolve it with a Gaussian. This is what a function of a Gaussian in mathematics looks like, right? This is a circularly symmetric Gaussian, which means its variance in the x direction and variance in the y direction is the same. That doesn't have to be the case. That could have been different, but we are using a circularly symmetric Gaussian. Okay, and so this is what it, as a picture, it looks like. That's a circularly symmetric Gaussian function. It's higher in the middle and it decays as you go. It's like a round hill, Shimla Pahadi, right? but that's not very round. It's a bit like really smooth hill. Okay, and so when I convolve the image, because Gaussian is just one function, when I convolve the image, I get something like this. Now, if my variance was more, I will get more blurring. If my variance was less, I'll get less blurring. But at some variance that I use, this is the image that I got exactly. Okay. And now what I'll do is I'll differentiate this image. This is really IXY convolved with GXY. So I'll actually take the derivative of this rather than original IXY. How do I do that? Well, that's really the same. I convolve it with +1 -1, but now this smoothed image, okay, to take its derivative. So it's really the partial derivative of IXY convolved with GXY with respect to X, okay? And this is what it looks like. Now notice that this is like more smoother, blurred out edges. The noise has been suppressed, but at the same time, there is a blur which is introduced, right? And similarly, I can do that to the second direction, and that will be the partial derivative of this convolved function I convolved with G with respect to Y, and that looks like this. So at every pixel, if I pick one value from the top image and one value from the bottom image, that will be the gradient vector at that pixel. Agreed? Yeah.
So if an edge is purely horizontal,
Yeah.
so it will appear in one of
Exactly.
one of the convolutions not given.
Exactly. If the edge is purely horizontal, it will appear in the vertical convolution, which is the x direction. It will have a non-zero value there, but it will have perfectly zero value in the horizontal convolution. Agreed? Yeah. And that will mean the gradient vector will be vertical because that direction has a value, the other direction doesn't have a value. Yeah.
So, when you're blurring it, aren't you just increasing the locality of the edge? So, let's say when you use a bigger mask, it's maybe the lower edge around 100.
Okay, so that's a good question. Using a bigger mask actually has some sort of averaging effect in it, incorporated within it. But this is the principal way to do it, right? I used an I used a I used a blurring filter because I wanted to suppress noise, and then I used an ideal derivative filter. The exact derivative filter that is mathematically motivated that this is what the derivative is. Agreed? So I perfectly mathematically understand both operations here.
The problem with the bigger mask is going to be
A bigger mask is that in the definition of the derivative, you should have a step size as small as possible. Then it is close to a derivative. If the step size is large, you are getting something like a derivative, but it's not really a derivative. Okay. All right. So the way to write this whole vector is that it's the gradient of I convolved with G. And G has a parameter sigma in it, so I just put a small sigma in the subscript. Okay, that's my way to write the whole thing mathematically if I want to. All right, now this is good, but instead of doing these two convolutions back to back, you realize that convolution, I mean, we didn't discuss this, but convolution actually is an associative operator like multiplication. Because convolution is formed only of multiplications and additions, and multiplication is also associative, and addition is also associative. So it's not that difficult to see that most likely convolution is also going to be an associative operator. Okay, which means that instead of convolving the image first with the Gaussian, like I did in the previous slide, and I got a result of that, and then convolving that result with your two derivative masks, you can actually do this. You can actually first find the derivative of the Gaussian in the x direction and y direction, and that will yield a mask. And then you do only one convolution with the image. I mean, one for each direction with the image. Okay, yani to get the x derivative, instead of convolving first with the Gaussian and then with the derivative, you can just convolve the Gaussian and the derivative together, figure out what that is. That's going to be the derivative of the Gaussian, and then just convolve the image with that. Why would I be interested in doing it in the second way rather than the first way? It,
we first had to convolve the Gaussian with the image with a lot of calculation, and then we have to separately differentiate the image coordinate for a lot of calculations. And in the second case, the number of calculations is drastically reduced.
yeah, in general that should happen. So really convolution, the convolution of the masks themselves is a tiny operation because these masks are not very large. The image is the large part, and so if you have, in general, if you have a lot of filters to apply to the image, and one after the other in a sequence, and you want one result in the end, you can convolve those filters together and just get one result together. Okay, and so instead of getting the gradient of image convolved with G, we can get image convolved with the gradient of G. Because of association, they should both be equal. All right. So that means we have to figure out the gradient of the Gaussian function. If we can figure out the gradient of the Gaussian function, we can just apply that to the image. Well, so I can take the partial derivative of G with respect to X. You can try this as an exercise. This is what it comes out to be. It's really, forget about the constant 2 pi sigma 4. That's just a constant term. It's really minus X times the Gaussian kernel itself. Okay, and this is what it looks like. I've shown it in 3D and as an image. This is what it looks like. In fact, this is exactly the function that I was showing you earlier as motivation for how the gradient vectors look like. And then I can do this in the other direction. This is the mathematical expression, and if I plot it, this is what it looks like. So that's it. I won't do those two separate steps. I will just take this mask and apply it to the image. Once, and in fact, these masks are just a transpose of each other. So I can just compute it once and then take its transpose and apply it to the image again. All right. Well, look at them. They are transpose. If I take this matrix here and I transpose it, I'll get this matrix. Okay, so as a matrix, it's just a transpose operation. Because we took a circularly symmetric Gaussian, then the derivative in this direction and the derivative in this direction is actually equivalent except for the direction itself. Okay, so it holds only for the circularly symmetric Gaussian, not in general. Okay, so that's the gradient of g. The gradient of g is going to be partial derivative of g with respect to x and partial derivative of g with respect to y. So now I will make an equivalent picture. Well, I'll take this image, but instead of first convolving it with g and then with the derivative, I'll just convolve it with the derivative of g in the x direction, and I get this result. This is actually exactly the same result as on the previous slide, even though I did it differently. I computed it differently, and I get this result, and that's it. Okay, and that's I convolve with the gradient of g. That's the x derivative and the y derivative. Okay, so now you have been like really interested about how should I combine these two derivatives to get one sort of representation for the edge. So here what I did was, well, gradient is a vector, so I can find the magnitude of a vector, and that would be like the total strength of the edge at that point. Okay, and how do I do that? I just take the L2 norm, which is for a vector xy, the L2 norm is x square plus y square square root, the distance formula also, right? So this is just the L2 norm of the whole x and y gradients, which is just the square of this x partial derivative, the square of this y partial derivative, and the square root of that. I plotted that here. This is what I get for this image, right? Now this is useful because regardless of whether the edge was in the horizontal direction or the vertical direction or anywhere in between, I still get a response here proportional to the actual strength of the edge. If the edge is in the horizontal direction, then one of the terms is high and the other is exactly 0. If the edge is in the vertical direction, then the other term is high, the other is exactly 0, right? If the edge is like, let's say 45, then both terms are like somewhere in the middle. But if I had a perfect circle and I computed edges like this, the gradient vector at each of the edge points, but then I computed the magnitude would come out to be the same regardless of the orientation of the edge. All right? Because it's the total length of the gradient vector, the total energy inside the gradient vector. Okay, so gradient magnitude is a very useful direction, is a very useful term. And now, you asked earlier, what about the effect of sigma? So here what I'm showing you is, this is the Gaussian function for sigma is equal to 1, sigma is equal to 2, sigma is equal to 3, and sigma is equal to 4. You notice that the Gaussian gets fatter and fatter. Okay, and this is the partial derivative of x, the partial derivative of g with respect to x. For sigma is equal to 1, it's like sharp peaks. It gets a little bit broad, a little bit more broader, a little bit more broader. So as I'm increasing sigma, there will be more and more blurring happening to my edges. In fact, I could have, if I have a very large sigma, the really sharp, thin edges might actually get just destroyed as noise. They might get averaged over. Okay, and similarly, that's in the other direction. Yes.
So the derivative with respect to x seems to be algorithm. How does that?
Yeah. Okay. That's it depends on how you normalize it. So if in a Gaussian, if you use the 1/2 pi sigma normalization term, then that normalization term ensures that whatever is the sigma, the area under the curve will be 1. Okay, so that's why as the Gaussian gets fatter, it gets the peak becomes low. Okay, if you don't use that constant, then the peak will remain at 1, which means regardless of the sigma, it will always rise to a value of 1. Okay, so this is the effect of sigma on the images. So here I have the image. This is sigma is equal to 0.5, blurred image. This is the original image blurred. No, sorry, this is the x derivative. Okay, so this oh, so my figure is a bit messed up. It's these figures are hiding this one under it, right? So, but this sigma is equal to 0.5, 1, 2, 3 in one direction, and sigma is equal to 0.5, 1, 2, 3 in the other direction. You notice that the edges get blurred and blurred, more and more fatter, and this is the gradient magnitude. So this is gradient magnitude sigma is equal to 0.5, 1, 1.5, and 2. Okay. All right. That's just to get you a visual understanding of what sigma does to your edges. So in this case, if there was a really sharp feature somewhere, like look at these lines here, they are almost lost in this image because sigma is too big for them. All right. All right. Now that was the effect. If I just make the magnitude, what does the magnitude give me? What does the gradient direction give me? The gradient vectors. So here I'm plotting all the gradient vectors of the image. Okay, so they are always pointing in the direction of maximum increase, right? So really in the middle of this picture there was a bright spot, so there is like dark spots around it. So from those dark spots the vectors are pointed towards this bright spot. Okay, they somehow know where to go to get to higher values. Okay, similarly, you see this kind of ridge here. So on one side the vectors are pointed this way, and on the other side the vectors are pointed this way, because from both sides they are trying to climb that hill. All right, so that's the notion of gradient vectors. In fact, gradient vectors are very useful because they tell me something about the structure of the image. So when we come to image features of trying to describe, let's say, a human person, or in self-driving cars trying to detect a pedestrian, we will see that gradient vectors, the direction of gradient plays a very strong role in that. All right. Here I've zoomed into one part to show you the gradient vector. So from the surrounding dark regions, they are pointed always towards the brighter region. So these ones are pointed this way, but these ones are all pointed inwards. Here you see that the gradient vectors are going from the darker side to the brighter side there, because that side is slightly brighter. It's a ball which has brighter shading on top. Here you see the gradient vectors are climbing towards the ridges. Okay, here you see that the gradient vectors are all pointed inwards, and here you see in the middle there are no gradient vectors. I've actually I mean I've just plotted the gradient vectors, but here in the middle the gradient is kind of close to 0 in the x direction and 0 in the y direction. So the vectors are really small, but from the edges there are long vectors coming in because there was dark region around the gray patch. Yes. So at every pixel, I compute the gradient. So it's at every pixel. So my gradient matrix is, there are two gradient matrices, one with respect to x, one with respect to y, and they are both as big as my pixel image, which means I have a gradient value at every pixel. So I pick the x value and y value at every pixel, and I just did a plot of that. So there is no other processing done here. This is exactly what I showed you on the previous slide. The x derivative of Gaussian, the y derivative of Gaussian convolved, and then plotted as a vector at every pixel. So when you say there is an origin, well, yes, because indeed every vector is from one pixel value. I mean, it has a location. This vector was computed at this location, so I plotted at that location. So MATLAB has a command quiver plot. That's what I used here to generate this view. Okay. Yes, you have a question.
I don't understand how you can figure out the direction by looking at only the orthogonal directions. If you look at only two directions, how do you figure out which was the steepest way to go? Like, I don't figure out how that's working.
Yeah, but that's just stems from calculus, right? So if you want to review that topic in calculus, the way you prove that in calculus is you first introduce the notion of directional derivative. The directional derivative is a derivative in one direction, any direction of choice, right? And so the way you do that is you take the dot product of gradient with the direction vector. Okay, so that allows you the notion of finding gradient in any direction rather than just in the x and y direction. So when you find the directional derivative, you have the gradient, which means with respect to x and y, dot product with the direction vector, let's say 1 0 or 1 1 or whatever, right? And then what you do is you say where will the direction derivative will maximized. So you try to pick the direction that maximizes the direction derivative, and it turns out that the gradient direction is the direction in which the directional derivative is maximized. So that's a very useful result. I'm just showing you, I mean, that result we have already seen in calculus, and I'm showing you how it's proved in calculus, right? Now, I'm just showing you the result of that, and it's actually quite amazing, right? The vector somehow knows where I should be pointing. Okay. Of course, it assumes local smoothness in the function. That's an underlying assumption. Gradients are defined. The definition that of the derivative actually assumes local smoothness. Okay, so if it was, remember I'm saying in gradient descent, the gradient direction points in the direction of maximum ascent. So negative gradient direction points in the direction of maximum descent. That does assume local smoothness. If there wasn't any local smoothness, it could be that the direction of maximum ascent is this way and the direction of maximum descent is this way. But that means there is a discontinuity in the function, if that's the case. Right? So this holds for continuous functions. Okay, so I mean, all your calculus that you have done is really useful. It's not just to forget, right? It's giving you like useful image features here, as we'll see. Okay, so the gradient direction I can write as an expression. You know, this is how you find the direction of a vector. You take tan inverse arctan of y over x. In this case, our y is partial derivative of phi with respect to y, and x is partial derivative of phi with respect to x. So that's your gradient direction. Okay, I showed you that image. If I color code that image, this is what I get. Now here I've plotted just the directions, not the actual vectors. Okay, so you do, even though I had 0 vectors here, I do get some directions here also, because even the smallest direction, the smallest vector has a direction. But what I can do is, often we do this, that I ignore those vectors. Dark blue here is I'm not going to use those values. Okay, so I ignore those vectors which were really small because their direction is arbitrary, and then I get a really nice representation of an image. Notice that all the parallel lines are in one color, right? The yellow color is like horizontal lines, and so on. In fact, there are 2 colors for these parallel lines. Why is that? Because one of them is the white ridge and the other is the black one. So on the white one, all the vectors are pointed inwards. On the black one, they are all pointed outwards. So they are like, their directions are 180 degrees apart. Okay, because there are 360 degrees, so their directions are 180 degrees apart. So that's why I have, in this it looks like. But notice that there is an orientation here to my colors with respect to the edges. Okay, yeah. No, not at all. There's nothing hot about this image. No, not at all. Not at all. How do night vision goggles or IR cameras work? They just respond to a different wavelength, which is the IR wavelength. So there are near IR and deep IR cameras that you can get. This is just a colorful image where I color coded the gradient direction. No, it doesn't really show brightness. It shows orientation of features. That's the important thing, right? Okay, so here's an example. For the image that I was showing you earlier, this is what the gradient magnitude looks like. Notice it's like very nice and clean. There were dots in the background, so each dot has a nice circle around it because it's magnitude. It's not direction, so it's magnitude, so it doesn't depend on orientation. Gradient magnitude is invariant to orientation, but gradient direction obviously is not, right? So so this is a continuous image really. There are zero values where, I mean, or close to zero values where there is no gradient, and then the bright values are where the gradient magnitude is high. In fact, if you look at it closely, if I enhance this image, I realize that I have values everywhere. Even these black regions have some value of gradient magnitude, and that's because there is noise everywhere. So there is some derivative everywhere, and that's why I have a gradient direction also everywhere, even though I can just ignore very small values if I want to. Okay, but what do I do with this image? So one way to do edge detection would be just to threshold this image, so that I get a binary image, and in the binary image, wherever there is +1, I say that's an edge, and wherever there is 0, I say not an edge. So thresholding means I just kept the values. I mean, I said t is equal to 10. So anything above 10 or above 10 is +1, and anything below it is 0. Okay, so I'll get this. Now this has a bunch of edges in it. If I increase the threshold, I said the t is equal to 20, gradient magnitude greater than 20 is an edge. Well, then I get less values. Okay, 40 I get even less values. 80 I get really less values. Okay, so that would be a very simple edge detector. Because the edge detector is supposed to tell me is this pixel an edge or not. So it is supposed to be a binary decision. So I came to this binary decision by thresholding the gradient magnitude. Okay, and this is the gradient direction for this image really. Notice how nicely you get like a whole lot of colors around the circle, because the gradient direction is really changing around it. This is that arctan f sub y over f sub x. Okay, so all the edges going this way are like red, and that way are like yellow, and so on. Every edge gets some sort of color. In fact, I didn't show you gradient direction at all places. There was a direction here also and direction here also. I suppressed it, saying if the gradient magnitude is close to 0, don't show that direction. Otherwise, this would have been a very noisy representation. You wouldn't have been able to extract the useful edges out of it. So I gave color coding only to the edges which had strong gradient magnitude. I color coded their direction 0 to 360 degrees. Yes? No, I'm plotting theta. Theta is equal to tan inverse of the partial derivative of phi with respect to x and the partial derivative of phi with respect to y. Oh, sorry, the other way around, y, x. So if this is your gradient vector, that's your gradient vector, right? So you take the second value of the gradient, divide by the first value, and take arctan of that. Okay, so I got a bunch of numbers in degrees, and I made all of those which were where the gradient magnitude was not large. I just made all of them green, and the rest I just color coded as 0 to 360 degrees. Okay, so I just used MATLAB's image SC command really, and chose an appropriate color map. All right. I'm showing you this picture so you get a sense of what gradient magnitude and gradient direction is. Now, in practice, there are lots and lots of edge detection methods. I just showed you the basics, the fundamental method to do edge detection. In fact, for a long time in computer vision history, starting from the 1980s, there was a very fundamental set of books by David Marr, a set of papers by David Marr, and then he wrote a book in 1978, 79, 80. And that spurred a lot of research in edge detectors, because people thought if we are able to make an ideal edge detector, we will then solve the perception problem, because perception edges are a fundamental thing in perception. And so there was a lot of years of research in perception in edge detection. And now then people gave that up, because like in the 90s, people realized that the texture information of the image has a lot of value also. So really the quest for an ideal edge detector was kind of suffered people gave up on it for about a decade or so on. But now with deep learning, people realize that we can have much more complicated edge detectors that actually perform very well. So I'm showing you a result from last year's CVPR. CVPR is one of the primary conferences in computer vision. The best work gets published there. It was happening actually this month in June. It typically happens like around 24 June or something every year. So it was going on last week, CVPR 2018. This is a paper from CVPR 2017. It's a very complicated edge detector. It's not simple filtering. In fact, this is based on deep learning. Essentially, at this stage, you can think of it as this is an edge detector in which we don't provide the filter like I did here. You actually learn the filter through machine learning. Okay, so this is a self-driving car. It's driving around. You see the original images here. That's the original video. Each edge is so the edges are what you see here, and each edge is color coded, and the color coding is between which regions this is. So, for example, building plus vegetation. That's the edge between building and vegetation. That's green. So that's why all these trees are green and so on. And the edge between vegetation and rider is blue and so on. So these are all the color codes. So not only are you getting the edge, but you are labeling, the network is labeling, uh, this is an edge between what and what. Okay. So actually it's quite impressive. And to be able to understand how this works, you have to wait. We'll do that in the rest of the course later when we discuss deep learning in Java. So this is just to whet your appetite. One might question here, if we discuss it from deep learning point of view, why are we finding the edges? Why don't we just directly learn the perception task that we want here, which is to identify persons and cars and so on? And that's actually a valid argument. I mean, a lot of people don't do this step. They don't try to build a very good edge detector, and then from that edge detector, they try to learn something. They actually directly learn the perception task, which is actually done here also. It's not just an edge detector. There's a perception task being done here also, which is what group does this edge belong to? Yes, question. Okay, so both tasks. I mean, finding these edges or finding the actual label of the vehicles and so on. Both tasks are now being done through deep learning, and so deep learning. So whether it's easier or not, I mean, at a broad level, they're both equally difficult tasks, right? Because of course, in some problems in deep learning are easier than others, but it depends on the way you do machine learning. You collect labeled data, so it depends on for which you have an easier time collecting labeled data. Okay, in this case, they actually mark ground truth of a lot of images, like is being shown here, and that's used to learn the labels. Okay, so we'll come to that. It's incredibly exciting. This machine learning shift in computer vision last 5-6 years is incredibly exciting because we are getting results, practical results. You are saying I have a library that can do this. Of course, that's what we'll discuss. How do you build these libraries? What's the mathematics behind it, or what's the strategy behind it? All right. Any comments? Questions? Okay, so I'm done with edge detection. The next thing that we will do is line detection. We will take these edges and try to fit lines to it. Okay. And then the next thing after that is corner detection. So edges, lines, corners, those are my primitives. And then we will talk about some higher level image features. All right. Okay, just for the purpose of announcement, if you guys have questions regarding the homework, we can have a tutorial at 2 o'clock. I mean, how many people want that? Okay, so we'll have a tutorial at 2 o'clock where I can answer questions. And then the homework is due tomorrow, right? The homework is due tomorrow. And then we will also, yeah, I'll announce the rest later. Okay, all right, thank you.